about efficiency. What is efficiency? A more efficient estimator is more precisely estimated and therefore has smaller standard error. So a more efficient estimate has better precision. To get efficiency, we need to so there is something called the Gauss-Markov assumption. Okay, the Gauss-Markov assumption. The first one is the linear model, linear in parameter, random sampling. Okay. The third one is full rank, which is the OLS2. The conditional mean of the error term given x is 0. So this is just a sufficient condition for the OLS1. Variance of the error term given x is a constant, which is a sufficient condition for OLS3, homoscedasticity assumption. So essentially, the Gauss-Markov assumption we already make, or is slightly stronger than what we have made. But if the Gauss-Markov assumptions are true, then the OLS estimator is blue, the best linear unbiased estimator, which implies that the variance of the OLS estimator is smaller than any other linear unbiased estimator. Right. So here the linear means linear in Y. Right. So the OLS estimator is also linear in Y. Right, because here's Y, not say Y square or log Y, right? It's just Y. So OLS estimator is linear Y, and the Gauss-Markov assumption says that if all the assumptions are true, then the OLS estimate has the smallest variance compared to any other estimator that also unbiased and linear in Y. Okay, and of course, that means the variance, the difference variance is positive definite. In general, it's the variance is a matrix, so it's the smallest variance means that the difference between OLS estimator and other estimator, the variance will be the difference in variance is positive definite. Oh, sorry. I just to note that when we say linear, you need to be a bit careful, right? So sometimes we say when we say linear, it actually means linear in Y. Sometimes we say linear is actually linear in parameters. Okay. So if we add an additional assumption that U given X is a normal distribution centered at 0 with a constant variance, so the variance is not a function of X. So this assumption actually means actually implies U and X are independent, right? Because a normal distribution only pinned down by the first moment and second moment. If both moments are not a function of X, that means any function of this normal distribution cannot be a function, cannot be correlated with any function of X. So this actually implies U and X are independent. So if you are willing to assume that the error term is independent from the X, then the OLS estimator have an exact normal distribution. We don't need to even so we don't even rely on asymptotics. The OLS estimate must follow a normal distribution. We condition on X because of course the OLS estimate the variance will be a function of X. So notation wise we need to condition on X. But that just means that essentially the OLS estimate follows a normal distribution. Okay. And that also means for each beta j head, it will follow a normal distribution centered at the true beta, so it's unbiased with a covariance variance matrix here. Okay, so the OLS estimate follows an exact multivariate normal distribution regardless of the sample size n. But to achieve that, we rely on a very strong assumption. We rely on independence between the error term and the x. And we assume that the error term follows a normal distribution. Right? Or essentially, we assume that y given x follow a normal distribution. Right? Because uh, because y equals x beta plus u. If u given x follow normal distribution, that means y given x also follow normal distribution. And this is a very strong assumption. Uh, so unless you plot your data, like say you plot your income with education, and if you do see that income given education is indeed a normal distribution, otherwise this assumption is likely to be false. Right? However, if you can make this normality assumption, then you don't need to rely on asymptotic. In fact, your t statistic and f statistic are exactly distributed as t distribution and f distribution. You don't even need a large sample size. Even with a sample size like 10, you are okay, as long as the normality assumption actually true. And with the normality assumption, we have even better efficiency. So adding the so there's something called classical linear model assumption. That is the Gauss-Markov assumption plus the normality here. So under the classical linear model assumption, the OLS and the maximum likelihood estimator are numerically identical. And we know that MLE is BU, best unbiased estimate. Because in this case, MLE and OLS are the same, so that means OLS is also best unbiased estimator. So best unbiased estimator means that the OLS estimator have the smallest variance among all unbiased estimator. So that's even stronger than the Gauss-Markov assumption because we add an additional assumption and we have even stronger efficiency results. So strictly speaking, the blue and blue indicate finite sample efficiency. Here we are actually talking about finite sample efficiency. So in fact, with OLS assumption 1 through 3, they already suggest that the OLS estimators are asymptotically efficient. When we talk about asymptotic efficiency, we needed to use this. We actually compare the asymptotic variance of this square root of n thing. Okay, and OLS assumption 1 through 3 actually suggests that the OLS estimator is asymptotically efficient relative to a class of estimator using linear moment condition. This one. Okay, and that means the asymptotic variance. So asymptotic variance of other linear, the asymptotic variance of other estimator minus the asymptotic variance of the OLS estimator is positive definite. Okay, so the OLS estimator is asymptotically efficient among a class of estimator using the linear moment condition. Right, so here is a linear moment condition. Right, because we don't have like say x like x prime log u, right? So it's linear. Here the error term is linear, and okay, so the error term is linear. Okay. Okay. So an example of such class of estimate is the instrumental variable estimator that we actually use e x hat plus u. Right. So again, U is linear here. Okay, and later we will see that indeed OLS estimator is more efficient than IV estimator. But of course, the problem is that the OLS estimate in that case could be biased. But anyway, so what I try to say here is to say, well, in undergrads we learn the Gauss-Markov assumption and also the classical linear model assumption, and that gives us the efficiency. Um, if we want, we can also talk about asymptotic efficiency. The definition will be a bit different, but it also says the same thing, that the OLS will have the smallest variance compared to a class of other estimators. In practice, we generally don't distinguish asymptotic efficiency from finite sample efficiency. The reason is because the variance estimate is the same. Right? We only have the same thing for the variance estimate. So whether you want to discuss efficiency in terms of finite sample, just use based on the variance, or if you want to discuss efficiency based on the square root of n of beta ham minus beta, but the variance is the same, right? It's just whether you have that n inverse there. We only have one estimator for the variance of the OLS estimate, so the distinction is mostly theoretical but not very important. What is more important, and what we learn here, is in general there is a trade-off between robustness and efficiency. There's no free lunch. You want better precision, you either get more data or you make stronger assumption. Of course, the stronger assumption could be true. That basically means your data is better. But there's no way you can get efficiency without making stronger assumption. Okay? But making stronger assumption means the results are less robust.